So the goal of this talk is to get to fusion in a practical sense. We talked a little bit about why it was worth doing it. And I'll just review it quickly. E equals mc squared. There's a lot of water. Other systems don't give us concentrated power, and there are the minimal nuclear proliferation and waste issues that are not achievable with a fission system. But it's been hard. Why has it been hard? The strong nuclear force is very short range. The electrostatic repulsion is a long range force and increases rapidly as you get close. So you need to make the particles move very fast to overcome that repulsion and allow you to get close enough to do fusion, which means high temperature, right? Quantum mechanical tunneling helps you overcome the potential barrier problem, but it's not enough. And of course, we're looking at the tail of the distribution function. I abbreviated a few of these things. So this is Maxwell-Boltzmann distribution of velocities. Fast-moving particles need to be confined for two reasons. One is to prevent their escape from the core if they're fuel. Obviously, you go to a lot of effort to make this hot tail. And then the waste, which is helium, alpha particles, needs to be kept around in order to keep things in the burning mode. So you don't have to get into the reheating process constantly. Now, as opposed to fission, however, you cannot have a runaway situation. If you lose confinement, all you do is shut things down. It might be local damage to parts of the machine, but there will not be catastrophic releases or anything like that. So again, quickly here, a number of these slides have the Spark logo on them. They come from Commonwealth Fusion's website and other material that they have. So they gave a talk a couple of times at the independent activities period for MIT over the last 2 years, and most of these slides were given in at that time. So here's a graphical example of what we're talking about with the Coulomb and repulsion and the strong nuclear force. So the ballpark number we're talking about is 100 to 150 million degrees. Now, confinement. You need to hold this stuff together for a long enough period of time that you can get useful energy out of it. And there's 4 ways to do the confinement that I know of. Basically, there's gravity, which only works on a stellar scale because in a star, the actual fusion density is very, very low. The output of the core of the sun is per unit volume is about the same as a human body in terms of energy. Inertial works with bombs and laser fusion, and it does work at, from bombs, we know, and laser fusion now has been demonstrated that it does work also. But the challenge of making it into a practical system for utilities is very large. And magnetic is considered to be the best candidate. And I said, well, there's a 4th one. Well, there are some crazy ideas that people have. And those crazy ideas include mechanical things bashing into each other. I mean, literally. It's a sort of a variant on inertial, but it's kind of strange. So how to confine the plasma magnetically? We take advantage of the Lorentz force on a moving charged particle. Lorentz force is basically the magnetic field exerts a force on a moving charged particle because the particle is charged, and as it is interacting with the magnetic field, it's producing its own magnetic field because of the motion of the charged particle, and those two fields interact, and basically the force is perpendicular to the motion of the particle across the field lines. You can think of it as if you have if you remember the old right hand and left hand rule stuff, basically, if the field line is your thumb, the particle will do the fingers around it. It depends whether it's an electron or an ion, which way it goes. So there basically are different means of achieving this now. The first one everybody thought about was just take a tube and squeeze it. And if you squeeze it hard, you get a pinch and you can heat the things up and confine things. There are issues that come about from that. And the obvious limitation is that particles that move along the field lines have no force acting on them, and they just keep on going until they run out of the machine. So the idea came along, somebody said, well, why not squeeze the magnetic field stronger near the ends, and then the field lines aren't quite going just parallel. They make a kind of a bend, and as they make a bend, there's a tendency of the force to act on the motion of the particle that's spinning along the field line and reflecting it back, and they called it a mirror. And that works. The obvious problem, of course, is that a particle really traveling straight down the center axis of the machine, where there is no curvature to the field lines, that will not be reflected, and it goes right on out the end. So various people came up with ways of trying to twist the fields and stuff like that. So you'd have a fan kind of going this way and a fan kind of going that way. And they were used things called Yuffie bars, which came from work in the Soviet Union. But mirrors were pretty much abandoned by the middle 60s for the most part. There were a few people still screwing with them. So the other way to do it is obviously take that long pipe and bend it around into a torus. And that was done beginning in the 1950s by people in a number of places, the most famous one being Zeta, which was a toroidal pinch that operated at Cullum Laboratory, actually began at the Harwell nuclear establishment in England, and they moved it to the new laboratory, Cullum. And the first PhD dissertation related to controlled thermonuclear fusion actually was done by someone who I met and knew very well at the University of Texas, who was an experimental physicist in the 1950s and became a theoretician because experiments got too hard, as he said it himself. So the other schemes were proposed in the United States by Lyman Spitzer at Princeton. He called it the stellarator. It sort of took the idea of the Yuffie twisted mirror and just kept on following it all the way around until you had this sort of multi-twisted thing coming around. And there is one of them at the Smithsonian Museum of American History in Washington, which was the figure 8 stellarator, which was achieved by just taking the torus and twisting the whole thing violently itself. Didn't work particularly well, but and in the Soviet Union, a number of people thought about the problem, and they came up with the idea of combining a magnetic field produced in the plasma with a magnetic field imposed externally. And it took several years to figure out the ratios of these things, but by the mid 1960s, they had a tokamak, which is a Soviet, not really an acronym per se, but it's a kind of a contraction of toroidal current machine. Problems come, however, when you have a lot of particles. There are macroscopic instabilities. That was the first thing that was seen in Zeta. There was something called a kink, which happens when you start to bend the magnetic field and because of the plasma. And as you bend it, of course, the field lines get tighter on one side and looser on the other side. So the bend keeps getting bigger and bigger until you hit the wall, and it caused the plasma confinement in Zeta to be extremely short. There's also something called a sausage instability, which can happen when things squanch down too much. And then again, it tends to link eventually to a kink or something like that. There's also just diffusion losses due to non-fusion collisions. Every collision that you have is not going to produce fusion. In fact, a very extremely small number of them do, but more than sufficient. But most of them are just bouncing off each other, and that can lead to enhanced loss across the field lines. And then there are charge exchange losses that happen because there's always some neutral atoms around, and a fast-moving ion can just basically the slow moving atom blunders into the fast moving ion, and the charges go boop and hop over and you end up with a fast-moving neutral atom and a slow-moving ion. And then there are radiative losses, which basically is if you have anything other than hydrogen in a machine, there will be substantial amounts of power radiated in X-rays, which will heat the walls and things like that. All this kind of came together in the 1950s again, when people developed what a physicist by the name of Lawson came up with a criterion, which basically is the minimum criteria for success, which is the original Lawson criteria was just confinement time and density sufficient to produce as much energy in the fusion as it took to heat the plasma to that temperature. The temperature was added in as a separate number, and then there's now a Lawson enhanced criteria, which basically includes temperature directly. So here's an example of a magnetic confinement, and it goes back to the sun. This is an eruptive prominence. There's the Earth, and this was
You need to switch slides, Ted.
Excuse me?
Here we go. All set.
Okay.
The slide was just behind you.
Oh, delayed. All right. No.
Sorry.
So there's the Earth right here, and here's a confinement loop. You can notice that first of all that this thing is toroidal basically, and you also see that there's twisting that occurs here. That this is light in extreme ultraviolet from probably iron that is looking like it's neon. It has had a lot of electrons stripped off it, but it's still relatively cold. There's many hotter parts of the solar atmosphere as go further out and stuff. We're now exploring this in detail with the Parker Solar Probe. So this was basically, as I said, about 10 years ago, March 30th, 2010, 304 angstroms light there, or 30 nanometers. And this is my attempt at superimposing a tokamak magnetic configuration essentially onto the solar eruptive prominence. And this shows you the path of a charged particle following the field lines in a very excessive manner, because typically the field lines this way are much stronger than the field lines in this direction. This is called the toroidal direction. This is called the poloidal direction. In the poloidal direction, the field is much weaker. So the field lines actually go around this way many more times than they do that way. And so this is an crappy artist conception of it, but can give you a sense of it to some extent. And by the way, there are two sunspots here of opposite polarity. So we're kind of back to the idea of the mirror almost in a sense. Eventually, these field lines can reconnect, and that can release energy to propel the plasma out of the area as a coronal mass ejection. So now back to a spark slide here. Here's kind of a summary of all this kind of stuff. You go from the solid to the liquid to the gas to the plasma as you heat things up. And the plasma, of course, is electrically neutral. It has just as many electrons as it has positive charges. The temperature involved basically is, as I said, 10 to keV or 100 million degrees Kelvin. Centigrade doesn't really matter. And here's your field lines now. They did a much better job of tracing the damn field lines. Again, the Lorentz force here. So if you Google tokamak on the website and ask for images, this is what you get. There might be some more. That was a lot, enough. And some of these are artist conceptions of things. Some of these are drawings. Some of these are photographs. And some of the photographs actually show you plasmas, though most of that is really sort of irrelevant plasma radiation. It's very low temperature radiation, typically coming from outside the actual part of the plasma that does diffusion. So going back to history now, this is tokamak T3. There was a T1 and a T2, but we have no pictures of them. I don't know what happened. The joke that I heard from a colleague who was in at that time the Soviet Union on a visit, he was told by a Soviet scientist the first two didn't do too well, and they were made as ice sculptures in Siberia. That's a Soviet joke. Anyway, this is what, if you heard the brick X house idea for Soviet engineering, this was brick X house type of engineering. Two things were very limiting of this. The Soviets did not have the way to make, except by painstakingly welding discs of stainless steel together, a metal bellows. Actually, a man from Sharon, Massachusetts, Ray Shamey, invented the method for making bellows using a hydrostatic system with an explosion inside of electrical explosion inside of a tank of water, and the shock waves formed the bellows, and he made a business out of it. And that was a breakthrough, because this thing had to have electrical breaks separating the segments, and that the electric fields across those breaks were very high compared to the electric field along the surface of the stainless steel. The other thing that they had a problem with was as you drive a current in the plasma, there's something called the hoop force, which is basically that the field lines inside the hoop are closer packed together than the ones outside, and the tendency is to spread the thing. So they came up with the idea of a shell made of copper, which would oppose any motion on a macroscopic sense. The tokamak that the group I was involved in, of mostly undergraduates, a couple of graduate students, and one postdoc, and a sometimes available professor at MIT, led to really the breakthrough in the sense of getting rid of the copper shell. In fact, my undergraduate thesis was equilibrium experiments on a tokamak without copper shell in 1974. In 72 to 80 timeframe, and I apologize, this is not Alcator A, it's Alcator C, which was a follow-on machine, very similar in many ways to the Alcator A machine, other than a little bigger and a little better job of packaging and stuff like that. Inside of this box here, this is a styrofoam box. Inside of this box is a liquid nitrogen cooled copper magnet. And it enabled you to go to much higher magnetic fields than this thing did. This thing has windings basically being fed right here. These are cables connecting to toroidal field coils, which are wound directly on the vacuum chamber inside the copper shell. Alcator A was successful, but it had some problems. Alcator C was better. And then that created enough interest that a much bigger machine called Alcator C mod, why it didn't call Alcator D, I don't know, but it didn't, grew up in its place at MIT. And that has directly led ultimately to the Commonwealth Fusion Company. Meanwhile, in Europe, in Culham, basically they hadn't abandoned toroidal machines entirely, and they took the idea of the tokamak from the Soviets, and they built a machine. They had built several smaller ones, but they built a big machine called the Joint European Torus. In 78, they started construction on it. In 83, they produced the first plasma in it. And in 91, they began working with tritium. So they became one of the first places in the world that actually could do real fusion, in the sense of if you put deuterium in a tokamak, if you heat it up enough, you'll get some fusion because the deuterium reaction is much harder to get going, but you always have a few tail of the distribution function things, and they'll bang together. So you get some fusion, but to get serious fusion, you have to put tritium in there. The minute you put tritium in there, though, you get lots of neutrons, and the neutrons make the experiment somewhat less good for graduate students because you can't go over to the machine any time you want to. You have to wait till it's been shut down for an appropriate period of time to allow the short-term radioactivity to dissipate. And then we get to this machine. You can't see the tokamak itself. It's in construction inside this giant building over here. This is the ITER, which was originally an acronym. And then they realized that ITER means the way or the path in Latin. And of course, the Europeans always love to use classical references. This is being built in the south of France in Saint-Paul-les-Durance. They began the project in 1990s. When will it be finished? Well, sometime. Right now, it is the largest construction site by dollar value and complexity inside of Europe, and probably one of the largest in the world. The tokamak itself, you'll see a scales comparisons of the size of these things in a few seconds. So what does a tokamak look like in the kind of a schematic fashion? This is a kind of a Soviet kind of era style, because very few of them really use these kind of iron loops of transformer cores like they used to. But the basic idea is you have a toroidal magnetic field, which is imposed by these coils, like these discrete coils in this case, or in the case of the Alcators, a continuous winding of copper plates. Unfortunately, I don't have a good picture. I had one, but I can't find it now, of the Alcator A. I'll try to, when I fix this up, so it can be viewed by somebody if they want to, as part of the link. I'll get that. But so the net result is the toroidal field coils basically impose a toroidal magnetic field. The plasma current flowing essentially along that axis produces what's known as a poloidal magnetic field, and that goes around this way, right? And then there are these additional coils necessary to control the motion of the plasma and to keep it from the hoop stress from expanding. Those are usually called a vertical field. Sometimes they call them plasma positioning and shaping coils, as this drawing does. And the key to this thing, to making it work, is that the current is driven by this transformer effect. So whether there's a big chunk of iron here or just a solenoid in the center, the effect is the same. Another version of the same thing, essentially. That's why this is kind of a kind of less. Those couple of illustrations came from a presentation by Pablo Rodriguez Fernandez, who is at MIT, but he also works with CFS. So this is why this talk is here now, and why billions of dollars of private money have been pouring into the fusion business. To a large extent, it's because of what's happened on this slide. So in this upper corner here, you see a test which was performed almost exactly a year ago of a high temperature superconducting material toroidal magnet prototype. So this would be one of a number of toroidal field coils that would be combined together to make a machine that they call SPARC. And it's not, it is an acronym, but it's mostly now no longer an acronym too much. Yeah, this came out of actually a study done as part of a student project under Professor Dennis White at MIT. When he found out about the high temperature superconducting material, a colleague of his happened to be carrying a piece of this stuff around in the form of a conducting package of layers of material that combined together enabled you actually to take the idea of the high temperature superconductors, which have been around for more than 30 years, and convert that into a practical way of making a magnet that could operate in the fusion environment. And he asked the students, can you make a machine taking advantage of this high magnetic field? And they came up with this idea as a student project, and then they incorporated it. And they've raised over $2 billion. The idea is, its shape is very similar to the Alcator CMOD. It's a D-shaped plasma, not a circle. And it has everything you need for a fusion reactor. It will be a reactor, other than the fueling will be basically done on a sort of a interim basis, rather than having a blanket that breeds tritium in order to make a continuous energy output of the thing. This thing will just be fed with tritium and gas puffs. And so there will not be a blanket, though there will be some test blanket material and stuff and various things. And this is the CMOD machine viewed from a number of different perspectives. Looked a lot on the outside like Alcator C. The inside of the machine has a lot of things that are common to tokamaks and a few things that are specific to the CMOD. This is the same view, except it's been unwound here. So you can see these things are all radio frequency launchers, of radio frequency wave launchers. The machine basically uses one kind of radio frequency waves to drive the current in the plasma, and another set of radio frequency waves to heat the plasma. And in 2016, on the last shot, believe it or not, the last shot of the machine before the Department of Energy said pull the plug on it, it set the world record for plasma pressure, reaching 2 atmospheres, which was achieved at a temperature not sufficient for really serious fusion. It was only 35 million degrees C, and it lasted for 2 seconds. It did yield a lot of fusion reactions, but not necessarily enough to be counted in terms of power output. And this was done with a toroidal field of 5.7 Tesla. The ultimate field of the machine was capable was 8 Tesla. Another view of the inside of the machine. You could, with difficulty, crawl inside that if you're a small person. There's a 360-degree tour that you can go to, and I don't know if this will work or not. See if it launches. Does it launch? No. Okay, so there are views of the lab. Inside the lab, outside the lab, and the control room. You have to have a control room. We didn't have a control room when we built the Versator tokamak. We just had a rack of some electronics right next to the tokamak. But upstairs, they had a control room. It wasn't nearly as nice as this one. And there's an actual plasma inside the machine. This is what happens when the plasma ends its career. It dumps onto what's called a diverter plate as part of the exhaust system for the helium ultimately. And you see some extra heating occurs there. Some of the power supply equipment. This again, copper cooled magnet, so hundreds of megawatts of power went into the magnet. Obviously, you couldn't keep the magnet, a cooled copper magnet. You couldn't keep that magnet cold and make energy usefully. So it's a dead end from that standpoint. But everything else, pretty good. So back to tokamaks again. 55 tokamaks were operating as of a year ago, January, maybe a couple more, a couple less. There've been about 170 built to date. I've personally had my hands on Alcator A, Versator, Alcator C, Versator 2, Rector, Pretext, and Text. So I've got a reasonable fraction of those I've had my hands on them. And question is, have we achieved fusion? And according to Pablo, yes. This break-even condition is a little bit more serious criteria than the Lawson criterion. We call it Q equals 1, and it says that there's as much energy released in the fusion as it took to heat the plasma to that temperature in a steady state. Right. Now we know a tokamak is, of course, a transformer, so it can't be a steady state, but that's what the radio frequency current drive is for, to try to achieve that. And if you look on this plot here, you'll see here's Alcator C over here, here's Alcator A over here, here's Jet, here's a French machine, the tokamak Fontenay-Hawes, and there's a machine at Princeton, another machine at Princeton, another machine at Princeton, and this is the Model C Stellarator, which is plotted here, but it's kind of out of the league of all the other things. And this is at the General Atomic Company in San Diego. This is the D3, which is one of the largest tokamaks that's operating currently. Alcator C mod is shut down, and Jet is still operating. TFTR is gone, and there's a couple other tokamaks that are not on here that could be. There's a Japanese tokamak, there's a Chinese tokamak, and a Korean tokamak that could be on here, but they're not. No. The goal is basically to get into this range. Ultimately, this is where the tokamak is current becomes sort of irrelevant in terms of the heating. The heating is all being confined due to confined alpha particles. Q equals 1 will get you to the point where you can say, yes, we have a tokamak that makes fusion on a break-even scale, but it's obviously not practical yet. This might be kind of a crossing this threshold here, might be equivalent to Enrico Fermi's first nuclear reactor in Stagg Field in the University of Chicago in the 1940s. Somewhere in the middle of this, around maybe Q equals 15 or 20, you can say, yeah, I have a reactor that I can sell to people. So one of the challenges is basically, when you look at these things, why not do something else that's cleaner than DD and DT, like D helium-3, and you see this is the P-boron-11. These things produce only charged particles. There are no neutrons. But you notice at temperature, this is a log scale of temperature in kilo electron volts. And we're trying to make a machine that can operate right in this range. And we have to be out here somewhere about 10x. That's out of the range right now. If you operate then in the DT regime, basically you can end up with a very simple relationship that says fusion power density is proportional to the square of the confined plasma pressure. Now, why is that important? That's important because that's very strongly dependent on the magnetic field. So there are limits to pressure. If the plasma pressure, if the magnetic pressure over the plasma pressure is positive, is negative, I'm sorry, if the ratio is inverse, then the plasma will be unstable. That's where you get all those problems with kinks and in tokamaks, they're called disruptive instabilities, but they're really kinks essentially. So then the question is, well, on this direction here, you need to increase your magnetic fields. And this line sort of defines where safety is. You don't want to run right at the safety edge, because then any little kink that comes along can cause you a lot of disruption. Here's one of the, there's a Japanese tokamak right there, JFT. So the limit is pressure is constrained by this ratio of these two magnetic fields, essentially poloidal versus toroidal. And there's another Q, unfortunately, which is a little q, which says that to be safe, you have to be operating down in here where Q is greater than a couple. There's something called an internal mode, which manifests itself as a sawtooth variation in the X-ray intensity. It's one of the things that I showed in my my PhD thesis, which was characteristics of MHD in the pretext tokamak. So this region right in here, you can have a Q equals 1 inside the plasma, but you really want to stay in the safe range. So that forces the strength of the magnetic field, or alternatively, the machine gets bigger. Here's back to Zeta 1951. There's the original kink right here. And this is a universe of all tokamak parameters as of circa 2020, and how close they were getting to the kind of relevant range of interest. But the relevant thing that we want to talk about for the last part of this talk is why they're building this giant machine on a relative scale in Devons. And that's because of this. Fusion power goes as the toroidal magnetic field to the fourth power. So if you can make that magnetic field strong, you can shrink the machine. All the other parameters, this being the radius, major radius. The fusion gain, which is another measure of performance, basically goes as a third power. So it's not quite as strong as this, but it's still extremely strong scaling. So this is Alcator CMOD. There's actual data from Alcator CMOD. This is the data from the last shot at Alcator CMOD. So here's what plasma pressure looked like. Here's what the temperature, there's that sawtooth or that internal instability. You can see it there. These are fusion reactions in trillions per second. And this is the heating power in megawatts. This comes from mostly from our radio frequency. And this is the plasma current. This part is giving you the heating from the ohmic part, but as the plasma gets hotter, it gets better conductor, and the heating effect of the current decreases. And here's the magnetic field strength here compared to Earth's magnetic field. So this is why that looks like a good approach. Here's the magnetic field. Here's the size of the machine. Here's the fusion gain plot. Remember, we were trying to get up here somewhere. So we're either operating at a high magnetic field and a reasonable size machine, or we're operating at a low magnetic field and a very big machine. And so for ITER basically chose to operate at 5.4 Tesla. because that was essentially close to the maximum achievable magnetic field with low temperature superconductors. Because remember, ITER, the design work on that thing started in the 90s. High temperature superconductors existed by the time that ITER was being designed, but did not exist in a practical fashion. So they chose 5.4 Tesla and a huge major radius. This is a machine you can drive a truck around inside. So here's CMOD. This is all to scale. CMOD, D3 at General Atomic, JET at Cullum, and here's ITER. And somewhere in one of these things, maybe not on this one, there's a person that you can use for scaling. And this is what the International Atomic Energy Agency thought would be the follow-on to ITER. I don't think this will ever be built, because this is going to end up costing 30 to maybe as much as 50 billion euros by the time they finish it. And this would be 200 billion euros. And even with kind of phony money these days and everything, that's still a lot of money. And you can see the size of the machine. It's just enormous. But this one can lead right here to something else. So this was a driving thing that the Spark guys used to raise money. They went to people, including an Italian energy company, and they said, if we're trying to substitute fossil fuels with something else by 2050, in the US alone, it would require 300 gigawatts of new installed power. And that means 300 of these demo reactor things at the 1 gigawatt electrical level in the US alone. That would be 300 times, let's say 100, be safe, 100 billion per unit. That's an awful lot of money. So MIT proposed this idea on the basis of this material. This is a high temperature superconducting magnetic material deployed in the way you can actually wind coils with it. The material itself is a very thin layer on multiple layers of other things that make it malleable and usable in a sense. There's silver, there's copper, and all this, but the net result is mostly it's stainless steel with a little bit of high temperature superconductor plated onto it. And this is what you end up with basically if you follow this other path. So this is the Spark machine. Again, these are all to scale. This is the Spark machine. It's not much bigger than the Alcator CMOD. It's about the same size as JET, though it doesn't have all these external big coils here. And that would be a reactor operating maybe in 3 to 4 years. And Q equals 2 could be by the end of this decade. And in parallel with that, they'd be designing this machine, which actually will produce electricity for the grid. That's the goal. This is called ARC. And you can see it fits easily inside the chamber of the whole machine. This can be built in a factory and put on a flatbed truck or a barge and taken to a site and installed. So here's some PR about these things that appeared in all sorts of different places. It appeared even on the Late Show with Stephen Colbert, the New York Times, MIT News, of course. By 2025, they want to demonstrate net energy. Well, they make 2025, I don't know. The major radius, 1.85 meters. It's not much bigger than Alcator CMOD. The minor radius is a little bigger. The strength of the magnetic field is 12.2 Tesla. Current at 8 megamps. The basic RF power to heat is 11 megawatts. So how much do you get out of it? All these things have been achieved in some machine somewhere. And this is what they hope to achieve Q greater than 2, they think they can get to Q of 11 maybe. This would be at a temperature of 10 kilovolts, 100. And they have a number of different estimates of performance, and they all basically say, yeah, you could get to Q equals greater than 2 for sure, certainly maybe 8 or 10, maybe even 11. Different models and stuff. So that's what they're trying to do. Then they want to get to arc, and arc will actually have a steam generator and a turbine and a generator, and we'll put power out into the switch yard, and they'll have some cooling water going through the condensers with some cooling towers. And this path takes you directly into there, assuming everything works out. And this was, again, the talk. There was a special a Journal of Plasma Physics issue devoted to spark, and they published openly all the information you want to copy it if you want to. Of course, there's various patents and stuff associated with the magnets in particular. Here's the test that was done last. Well, the first tests were done in July, and then the official test was done right around now, essentially a year ago. So here's some stuff about, they got $1.8 billion starting in, I guess, December. This was give the inertial confinement people their credit. This was the breakthrough of ignition, they claimed, in this microscopic little pellet at the National Ignition Facility there in Lawrence Livermore. And then this was jet smashing its own record. Again, here's T3 again. Some more T3 pictures. I think these are after a team from Cullum came there with some lasers and measured with Thomson scattering the temperatures that people didn't believe the Soviets originally. Alcator CMOD control room. So this is where this project is being done. This is Route 2. Follow where we are right now in Lexington. Just go for about 30 minutes. And the old Fort Devens, right off the main drag off Fort Devens, probably be renamed because it's named after Thomas Stonewall Jackson. So if you sneak up closer, you can see this. They have a site, 47 acres. This is actual Google Maps picture of that site. And this is the actual reactor construction area. This is what the building is going to look like. That's the main building for the reactor itself right there. 4 lobes. There's a big building for motor generators over here. And there's some cryogenic storage tanks and stuff like that. Again, compare that to this actual construction site. This is what things will look like. This is the magnet assembly building where they're going to be building the magnets and selling them from here. And they'll probably build another building to actually package the magnets and make them into reactors and sell those. But that's not here yet. This building is well under construction. That was taken about almost 6 months ago now. And this is the reactor site. And that's what the campus will look like. This was a nuclear news as of May 16th that MIT agreed to basically become a subsidiary of Commonwealth Fusion Systems. They don't say exactly how much, but for 5 years, essentially the work that the Department of Energy was funding is essentially going to be funded by Commonwealth Fusion, though there's still some Department of Energy money. Right? And then they signed an agreement with the United Kingdom Atomic Energy Authority in July, so just over a month ago. And this basically makes sort of a kind of a bizarre way the UK a colony of the United States. There's a fair amount of money will be coming to the UK Atomic Energy Authority. Here's some close-ups of the superconducting materials. This is the result of testing in a facility in Austria, I think. And this is after they cycled it a bunch of times to see how it behaved. More information on the superconducting materials. And this is the kind of agreement with JET, access to the non-tokamak fusion technology facilities and contribution to experimental program planning on those facilities, collaboration on fuel cell cycle technologies, neutronics modeling, system integration models, advanced manufacturing, remote handling. All this has been done, a lot of work at Cullum. And they're building another machine over there that is basically a test machine to be connected with ITER, but it now will also be connected with Spark. And then risk reduction, basically. There's another machine that's being built over there that's a spherical tokamak, where essentially you take away the the wasted space in the center. Couple more pictures, I think. That's it. Okay, so that's it. Anybody has any questions? We're happy to talk about questions.
Yeah, Ted, this is Larry Whittick. About 6 months ago, maybe less than that, the Swiss National Lab did release some information that said that you could double the Greenwald limit, which has to do with instability, and still have a stable machine. I was just wondering whether Spark is commenting on that at all.
They are acknowledging the fact that there are various things that are extensions to the sort of traditional kind of catechism of tokamaks, which is based on those 150 odd machines worth of learning, and that new things are coming along and can improve things. But as of right now, the focus of Spark is to follow the path laid out in that journal issue of nuclear fusion or plasma physics. I'm sorry, and so there will undoubtedly be ways to improve on things, and some work, in fact, with the General Atomic, they're funding some work down there too at the D3 machine, which is being enhanced for some of its functionality. In fact, there's some MIT plasma physics people who are working at D3 now that the Alcator CMOD is shut down. Whether Alcator CMOD or something else pops up at MIT is unclear, but that speculation is that there might be something there that will be connected with Spark. Of course, it's 30 minutes and a little bit from Cambridge on the highway, and it's even achievable on the commuter rail. If you go to take the red line to Porter Square and then hop on the commuter rail, in an hour it can be at Spark. So there will probably be a shuttle bus, but run by MIT, I'm sure, as well.
Ted, I'm trying to put this in perspective. You were talking about the billions raised. I didn't follow every number, but the NASA budget, I'm trying to compare it to space exploration.
Yeah.
The NASA budget is $22.6 billion per year.
Yeah.
How does that compare to expenditures? I mean, if you think of the importance of energy versus space exploration,
right?
How do the numbers compare? Because you said a lot of numbers quickly.
Okay, so the budget of the magnetic fusion office of the Department of Energy basically has been almost constant in constant dollars since I stopped working on this thing, basically now 30 almost years ago. And we were subject to a amendment that came through that capped the growth in spending to inflation. But the reality was, of course, it didn't, because people were getting bumped into, higher salaries and more benefits and things like that. So the actual budget was shrinking. And the Department of Energy claims that there's a $1.5 billion going into just operating funds as opposed to building machines in the fusion budget right now. The National Ignition Facility thing is a separate thing that's funded to a large extent by the nuclear weapons programs, because when they stopped shooting off underground tests, they needed some way to keep testing the basic parameters involved in making a hydrogen bomb, and the National Ignition Facility does that primarily, and then it does commercial fusion on the side. So you could probably say that there's governmental money all around the world is probably in the 5 to 7 billion range. It's hard to say how much China is spending. They're not really telling us. And some of the other programs are a little somewhat hidden, but the UK, the United States, Japan, Korea, and now the European Union, they're basically in that range, 5 to 7 billion, and in the United States. So maybe if you count everything coming in from governmental sources, it's close to 10 billion a year.
And the private side?
The private side is now growing fantastically rapidly. Last year there was over 2.5 trillion raised in investors' funds, and the majority of that went to the Commonwealth Fusion thing. But
did you say billion or trillion?
Billion.
Billion.
Yeah.
So we're spending a lot more money sending Artemis around the moon.
Yes.
Than we are on nuclear fusion.
Yeah. And
does that make sense?
No, I don't think it does. I got into fusion. I got into fusion because of the idea of making a fusion drive for space transportation. That was my interest in when I was in high school. Was can we make a fusion propulsion system?
Jerry, that's not a fair. That isn't a fair comparison.
Excuse me, Michael.
Yeah.
Carl's had his hand up, and let's try to do things civilly, please.
Okay.
Yes. Thanks, Peter. So I don't know, Ted, if you can possibly answer this question, but I am curious about how Commonwealth Fusion is already doing so much construction of sort of manufacturing facilities when they haven't really proven, and they expect to take another 3 years or so to show that their thing actually works. And you would think that along the way, that even if they do make it work, they may discover that they have to make various changes. So it does sound to me like it's very premature to build manufacturing facilities, though I realize that, you could make a bet that maybe it'll all turn out to work and that'll speed up the ultimate process. Do you have any comments on that?
Yeah, well, the manufacturing facility that they're building right now, which will ultimately sell things to people, is making their own magnets. So in order to build Spark, you have to make a bunch of these things. And they're going to build, there are going to be 16 in Spark, and they're going to build a number of spares and some used for other purposes as well. So they may be building, 25 or 30 of these things, maybe 40 of these things, and they need a building in order to do that. So the building that's the manufacturing plant is a magnet manufacturing facility. They're currently building them by hand in the facility in Cambridge. And this is an automated means of manufacturing those kind of magnets. So the thing that wasn't obvious maybe from this presentation is if you look inside of this thing, this is basically a cryostat. And if you look inside of this thing, there is a piece of picture somewhere. Used to have one. So this is actually the coil material for the toroidal, for the transformer for the poloidal central core. The actual coil winding is a flat tape for the pancakes that form the toroidal magnets. Right, the toroidal magnet right here. So those are made out of flat pancakes, and they're kilometers of this high temperature superconducting material, which is deposited by somebody else. And they buy the raw stock essentially, and then they have to splice it together into connections. So this is an example of splicing for the poloidal coil. Where is it? Somewhere here. Lost it now. But splicing is very important in order to connect the pieces that are not long enough by themselves. So you need a big manufacturing facility to do all that kind of stuff. And they have created a opportunity here. They took a company that, you know, this stuff here. So this is an example of a splice here between two sections. This happens to be for testing purposes, so this is a much bigger block than normally would be used. But they took a company that was building in Devens for biotech companies and for some other companies facilities, and they said, here's the deal. We'll buy the land. We'll then basically have you guys build this building, and we'll lease it from you. So the investors are protected in the sense, if things don't work out, this is a very nice facility that King Street Properties basically can market to somebody else. So I think that's the mechanism for why they're doing it the way they're doing it. And they're trying to do it on a very fast track basis, so that when this building is finished in the next couple of months, this building will be finished and it will start manufacturing coils in here. Yeah. As opposed to ITER, where, you know, their pieces are coming from all around the world, and they have a warehouse that's the size of well, I don't know, an airplane hangar or something like that, just storing parts for ITER. You know.
Thanks.
This building over here, yeah.
Dick?
Yeah, Ted, if I can go back a bit to some of the basics of what's going on with
Sure.
trying to get fusion power to be useful in terms of our electrical grid and so forth.
Yeah.
I've always been wondering how it is that you can keep any fusion reactor running long enough so that you can extract for a period of time, for a decent period of time, the amount of energy that you need in order to be useful to the industry or to our uses. And the problem that I have in thinking about the physics of this is that you're putting in KeV energy to get the plasma at the proper temperature so that you can get fusion. But what happens is that the reactants are at MeV energies. So now you've got a tremendous amount of energy being liberated in the fusion reaction. And I'm wondering how you can keep this reactor running at a long enough time so that you can do this on a commercial scale.
Well, JET right now has got the record in two kind of ways. One way, in terms of power output, they achieved about 16 megawatts peak power output back in 1997. They were very close to this Q equals 1. And most recently, they have increased the power, the energy output, but not the power output. So the peak power output dropped a little bit, but they made 59 megajoules worth of fusion energy. 59 megajoules in a pulse that lasted about 5 seconds. Okay, that's Q equals 0.7 or something, maybe 7.5. If you were to scale that by just saying I can go a couple of steps in size up on jet, or I can increase the magnetic field a little bit, jet can get to Q equals 1. But the problem is you can never make a commercial reactor out of it because of those big monstrous copper coils that consume hundreds of megawatts and limit the pulse length because the magnets would melt. So if you replace those magnets, you know, if you could take jet and just replace the magnets with superconducting magnets and push parameters a little bit, you're right there to do the Q equals 1 point something.
Yeah, but the thing that bothers me is that this is only a very short period of time that they've achieved this Q value. You're not able, I mean, from what I can see, you're not able to continuously keep that up, which you would need for a commercial process.
Yeah, so that's an issue, obviously, in terms of the practicality of the thing,
right?
That the pulse has to be dealt with in some fashion. Now,
Right.
The pulse right now is limited by two things. One is the toroidal magnet energy that comes from a big rotating machine that's dumped into the magnet. And you know, if you remember what a wood chipper sounds like, this was a wood chipper on steroids at MIT or at the University of Texas. You'd hear this thing a block away when it would
Good
fire,
luck.
basically. But if you get rid of that limitation, so you go to the superconducting magnet, then you still have the limitation of the current that needs to run inside the plasma. And that's what the stellarator people are always laughing about. So if you have the current limitation, because you've got to have flux changing through that central core through here, you have to have flux changing through here in order to drive the current. And eventually you run out of flux changing that can happen. The voltage of the so-called loop voltage drops to a very low value, and the heating efficiency is dropped very low in any event because the plasma is a very good conductor by then. So then you need something else, and that's where current drive of some other fashion. So some people are talking about shooting in neutral beam currents and getting some fusion in what's called a wet wood burner mode. And other people are basically using a particular kind of radio frequency current drive that has been tested on a number of machines, including the Alcator CMOD. And they can extend the current because you don't have to have the flux change in the core from the external field. You end up with it driving a current and from another source, so the flux change in the core of the transformer can go to 0. Then, in principle, the discharge can last as long as it wants to.
Yeah, I had just recently heard about this kind of on and off kind of a procedure in order to keep this thing running.
But the other thing, of course, is when you get to this model right here, where is it? Yeah, when you get to this model right here, this is decoupled really from what goes on inside. So you could, in principle, build a plant where this thing pulses every once in a while, and as long as this temperature in here in the blanket is sufficient to keep making steam, you keep on driving your generator. Now, a lot of utility people don't like that because of the pulsing part, but
Yeah.
those are issues that will be dealt with in the next next couple of iterations of things. Whether ARC is actually going to be a machine that puts power out into the network, I don't know. That's unclear. But they still, they believe that's the case if you follow the path from Spark, and if Spark does what it says it's going to do in the next couple of years.
Alan?
Yeah, Ted, is Spark going to include the neutron generating blanket, and what's that made of?
Okay, so blankets are a topic of hot discussion, if you pardon the pun. You absorb your neutron, and basically the premier material to absorb the neutron is to absorb it into lithium-6, which basically then has a nuclear reaction and produces more helium gas and tritium. And that basically, then you extract the tritium from the blanket and you put it into the tokamak. The amount of tritium involved is trivial amounts. It's grams, basically. So people are worried about tritium. The inventory will be, a few times the amount that's in the machine, but it won't be very large. And it will, of course, if it escapes to the environment, it's just going to rapidly oxidize and become water, and eventually it will dissipate in that sense. So, but the blanket is not going to be a major factor in Spark. Spark will basically not be constrained by making enough tritium to run it. It will be running as a power source, in the sense of a source of heat, but heat be dissipated to the environment. There's not going to be any useful function from the heat, so they won't run it, just for the hell of it. They'll make some long test runs, obviously, to show that it stays together when you run it for a long period of time and stuff. But the goal of it is really to show you can make several hundred megawatts of heat, and then you figure out how to make that into something that you can make into a steam plant. So Spark will not have a blanket that's designed to capture all the neutrons and produce enough tritium to fuel itself. It will probably have some blanket test material in there and stuff like that. Their current thinking is a liquid blanket. You go, well, liquid lithium, well, that'd be great. Problem is, liquid lithium is a very good conductor, and you're dealing with these enormous magnetic fields, and that would make the task of pumping the liquid lithium around and stuff very hard. So the current thinking is some sort of a salt that melts at a reasonable temperature. That's a lithium and possibly beryllium salt of some variety, and they're working on some ideas, and it would probably be a ceramic jacket with this liquid metal salt flowing around, which is not a good conductor, flowing around inside the toroidal magnetic field coil. So the blanket in ARC is this in here, right? So there's the layers of this thing is a little hard to unpack, but and that essentially means that you don't have to do that right now. That will be done along the way. ITER will have spaces in it for testing blankets, and they've put out contracts for blankets being developed by Korea and Japan and the United States. I'm not sure if the UK is in on blanket design. I think it might be, but.
And what happens to the tritium that you generate?
Okay, so the tritium you generate is useful. That's what you want for putting back in the machine.
How are you going to get it out of the ceramic?
Well, if the ceramic is essentially a porous porous ceramic with this liquid circulating through it, the thinking is somehow or other you have a barrier somewhere in the system that on one side is the liquid material circulating, and on the other side of it is kind of like a gaseous diffusion plant at Oak Ridge. On the other side of this thin barrier is tritium coming out, and helium as well, because helium comes out as well. So you have helium and tritium coming out, and then you know just ordinary chemical separation basically separates those easily. And as I said, the amount of tritium that's in the machine when it's fusing is grams, and maybe it's 100 grams that's circulating around in the entire inventory of the entire plant or something like that. So you may have a storage facility where you store liquid tritium or something like that.
You'd have to scavenge it because it has a half-life of 12 years, something years.
Yeah, but you will be basically one thinking would be, for instance, if you have this material coming out of the reactor part of the in this area here, that material basically on its way to the steam generator is cleaned up so that the stuff that goes back into the machine goes this way. Actually, the stuff that goes back back into the machine is stripped of the lithium. Of the tritium and the helium, and you could do that with some sort of a carrier gas that would blow through the liquid and blow through the bubbles in the liquid or something like that. But that's still to be developed. That's a lot of work, and the fusion center at MIT has actually restructured itself in the last couple of weeks to take more of the nuclear skills that came out of the nuclear program at MIT, and which is one of the best nuclear programs in terms of reputation, and use that part of the nuclear engineering department that hadn't really been tapped too much, and include them into this overall project, and let Spark pay for it basically. And then of course also the same thing with the agreement with Cullum to take advantage of the skills that Jet has developed in those areas. So I think they're covering the bases pretty well. And with the 1.8 billion, they don't need all of it to build a building. The project is $100-something million of construction.
Mike, then Ken.
Yeah, I have three things. The longer this ran, the more questions. First thing, small thing, you're talking about using beryllium, and it would in a situation in which it could actually be released where there are people. Beryllium is incredibly toxic and has to be controlled. The second thing is a question. Do you have any idea what the temperature is of the magnetic coils? Is it they just going to run liquid nitrogen or what?
No. The coils are actually going to be cooled with gaseous helium, not liquid helium, but gaseous helium.
No, I meant liquid nitrogen.
Sorry.
I said I was saying liquid nitrogen, not helium.
No. I'm saying the coils are not cooled. They are high temperature. They are high temperature superconductors, but they're not cooled just to liquid nitrogen temperature. Actually, to get this high magnetic field, you need to cool the magnets to closer to the temperatures of low temperature superconductors. But you don't need to be at you don't need to be at 5 degrees C. You can be Kelvin. You can be at 20 degrees Kelvin or something like that. And you can do that with gaseous helium.
Okay. Yeah, I've done that. Okay, and then the other thing was the question of comparison with a NASA budget. I just want to point out that NASA is more than just space probes. It has its budget is mostly not in going to the moon, but is in things like weather satellites and geodetic surveys and things of that sort. So it's a huge and very diverse operation. So I think as far as Jerry's comment is concerned, I think it's really off base.
Well, I mean, obviously, those are two very hard to compare circumstances. I mean, the Commonwealth Fusion has filed a bunch of patents on some of the magnet technology. And they've said that some of the other applications of those magnets could be for things like MRI machines, for instance, and other things which currently are handicapped by the use of low temperature superconductors. So you would be freeing up resources really in other ways too. So is that part of the business plan? I don't know. It might be, but they've certainly included it in some of their patent filings.
Yeah. Ken, go ahead.
I had two questions. First one is about the magnets.
Mhm.
Do you know whether they depend on rare earths or other resources which are not easily available in the United States? Is my first question. And second one has to do with the economics of the final arc model. I'm so impressed by the compactness of the cell, but it doesn't mean that it needs to be a large power plant that's distributed as power is distributed today. It could be a much more compact kind of power plant that's located right in the city. And
absolutely.
you don't have all the transmission lines, and the distribution system is completely different if it's so compact. So I wanted to understand better the economics of that and how that's envisioned.
Yeah. So the first part of that question basically is that it does involve REBCO, which is rare earth, barium, copper oxide materials. There are a number of high temperature superconductors. I think there's one of these things there that talks about it. Okay, so if you see this is the cable for this Viper cable, which is what they're winding the coil that goes in the center. Not the same as the tape stacks that are used for the toroidal field coils. But if you look right in this little block in here, this is the so-called HTS stack. And inside there are layers of stuff. And I thought I had one, but here's one right here. So if you can see this, you see this tape is constructed out of copper. This is high temperatures, high strength stainless steel. And then there's this stack of very thin layers, and then there's some silver, and then there's copper on top of it. And the whole thing, if you can see this is microns of copper, almost almost a millimeter between the copper and less than a millimeter of this and the stainless steel, and then very thin layers of this stuff in here. The actual REBCO stuff itself is on the order of hundreds of nanometers. So yes, there are rare earth materials in there, but the quantities are very small.
Great.
Yeah.
And then what are your thoughts on the economics of distribution of the reactors?
So the goal of this reactor, and this is the key thing, Dennis White really asked the students, make a reactor that we can put in the city, essentially. So this is this design for ARC, and it could change a little bit over time, is 200 to 300 megawatt electrical, which is in the 500 or so megawatts thermal, based on this kind of a thermal system, which gives you about 35-40% efficiency. So somewhere under under a gigawatt thermal, which basically is easily compatible with city. I mean, if you look at the facility on the other side of the street from the casino in Everett, right? That facility is over 2,000 megawatts electrical output. And obviously a fair amount of that is dissipated as heat after you've done all you can with it from the steam side of things. So they're probably pumping out 3,000 megawatts thermal or something like that, either into the air or into the river.
Larry, unless you have something really, really quick, it's 11:50 and we've stretched this a bit and people I think would like to move on.
This is quick. To answer Ken's question in part is as far as securing the tape, I think CSS already has, or CSFS has under contract already all the tape all the thermally high conducting tape that they need for building the Spark machine. So that supply line is under control.
Yeah, they've done a lot of work in that area. They've hired people from industry way outside of the realm of fusion, and including a person who was involved in the early work in building the rockets for Elon Musk with SpaceX. And manufacturing is one of their big emphasis. So they're looking into supply chains and all the things necessary to make it into a functioning business. I mean, even with some wild and crazy venture capitalists out there, you don't get over $2 billion in investment if you don't have a pretty solid business plan. I mean, yeah, of course you can make mistakes and stuff, but one of the investors in the thing is the MIT engine, which is MIT's specific sort of incubator for what they call tough tech or hard tech or long tech, where you have projects that take a lot longer than the venture capitalists are typically happy with. And then you've got contributions from a number of the super rich people as well. So those people are also probably unlikely to put their money in unless they see that there's a pretty good business side of this thing worked out. Now, admittedly, all of the top people in the company right now have PhDs either in nuclear science or in plasma physics. So there could be some issues.
Ted, thank you very much.